Have you ever tried to fit all your groceries into a single bag so nothing spills out? That's basically what satisfiability is about. Finding just the right combination of truths and falses so everything fits and works. In this lecture, we'll uncover why satisfiability lies at the heart of computer science, look at how we formally define these puzzles, explore the clever algorithms that crack them, and see real-world applications from AI planning to hardware verification. By the end, you'll understand not only the theory, but also how it powers everything from route optimization to cybersecurity. Ready to solve some puzzles? Let's dive in. To unpack that pivotal question, let's first define two fundamental complexity classes, P and NP. First, P is the set of decision problems that a deterministic Turing machine can solve in polynomial time. Practically speaking, these are problems for which we know efficient algorithms, ones that always produce a yes or no answer within a time bound that grows reasonably, think n squared or n cubed, as the input size increases. Next, NP is the class of decision problems solvable by a non-deterministic Turing machine in polynomial time. Equivalently, NP contains problems where, given a proposed solution, a deterministic machine can verify it quickly, even if finding that solution might require exploring many possibilities. Together, P and NP sit at the heart of computer science's biggest open question: can every problem whose solution can be verified quickly also be solved quickly? Building on our discussion of P and NP, let's now dive into nitrogen monophosphide hard and NP complete. A problem is nitrogen monophosphide hard if every problem in NP can be transformed into it in polynomial time. In other words, it's at least as difficult as the toughest NP problems. NP complete takes this one step further. Not only must a problem be as hard as any NP problem, it also has to belong to NP itself. That means nitrogen monophosphide. Complete problems are exactly those NP challenges that are as hard as any other NP problem. And here's a key point. Hardness transfers through polynomial time reductions. If you can reduce an NP hard problem P to another problem Q, then Q inherits nitrogen monophosphide hardness as well. The diagram on the right illustrates this relationship. NP is the large set, P is a smaller subset, and nitrogen monophosphide complete sits right at the intersection of NP and NP hard. Building on our last point, we now capture the essence of NP completeness through polynomial reductions. On the left, the large oval represents NP, and inside sits problem P, which we already know is nitrogen monophosphide hard. The arrows leading from P into Q on the right illustrate a polynomial time reduction. Every input instance of P is efficiently mapped to a corresponding instance of Q. The red region inside Q's oval highlights that these mapped instances form just a special subset of Q's entire input space. Because P is at least as hard as any problem in NP, and solving Q would let us solve P, Q must inherit that same nitrogen monophosphide hardness. In other words, whenever P is less than or equal to PQ and P is nitrogen monophosphide hard, Q is nitrogen monophosphide hard too, completing the core argument for nitrogen monophosphide completeness. Now, building on our discussion of polynomial reductions, let's turn to the Boolean satisfiability problem, or SAT. SAT asks whether there's a way to assign true or false to each variable in a given Boolean expression so that the whole formula evaluates to true. In the worst case, you might have to try all 2n possible assignments for n variables. For example, take this formula: not x and not z and not w or x and not y or not y. The key question is, can we pick truth values for x, y, z, and w that make this expression true? Finding that assignment, or proving none exists, is exactly what SAT is all about. Now, let's recap what we know so far. First, determining whether a Boolean expression is satisfiable, that is, whether there's some assignment of true or false values that makes the formula true, is an NP-hard problem. We often deal with propositional formulas built from negations, conjunctions, and disjunctions, which can get quite complex. To keep things manageable, we focus on expressions in conjunctive normal form, or CNF. In CNF, a formula is structured as a conjunction, a product, of clauses, where each clause is a disjunction, a sum of literals. The key insight is that any Boolean expression can be transformed into this standard form, allowing us to apply consistent solving techniques. Building on what we've covered, let's walk through this diagram step by step. At the very top sits circuit SAT, which we reduce to SAT and then transform into 3CNF SAT. Notice that this conversion is highlighted in the center as our pivotal move. From 3CNF SAT, the diagram branches off in two directions. On the right, we go straight to subset sum. On the left, we head into click, then onto vertex cover, followed by ham cycle, and ultimately the traveling salesman problem. The main takeaway? Once we've pinned down CircuitSat's NP completeness and mastered the SAT right-pointing arrow 3 CNF SAT step, we can unlock an entire landscape of classic nitrogen monophosphide complete problems via polynomial time reductions. Now that we've seen how SAT reduces to 3CNF-SAT, let's take a closer look at 3SAT. 3SAT asks, given a Boolean formula in CNF where every clause has exactly 3 literals, decide if it's satisfiable. To prove 3SAT is as hard as general SAT, we start with any CNF formula and reshape each clause so it contains exactly 3 variables. Since 3SAT is just SAT restricted to 3 literal clauses, this transformation preserves satisfiability. For example, take the formula: not X and X, or not Z, and not W or X, or not Y and off X, or not Y or W or Z. We can split the 2 literal clause X or not Z and the 4 literal clause X or not Y or W or Z into chains of 3 literal clauses by introducing fresh gadget variables. The result is an equivalent 3SAT instance that is satisfiable exactly when the original formula is. Continuing from our previous example, let's prove that 3SAT remains nitrogen monophosphide complete by converting any SAT instance into an equivalent 3 literal per clause form. Take an arbitrary clause, C equals X, or X, or X, and handle it in 3 cases. If K equals 3, we leave C exactly as it is, no change needed. If K equals 2, say C equals X or X, we introduce a fresh helper variable Y and replace C with 2 clauses, .X or Y, and X or not Y. No matter how Y is assigned, at least one of these clauses has the same truth value as the original 2 literal clause. If K equals 1, say C equals X, we bring in 2 new helpers Y and Y, then form 4 clauses, .X or Y, and X or not Y or Y, and X or Y or not Y, and X or not Y or not Y. This exhausts all combinations of Y and Y, so the whole block is satisfiable exactly when X is true. In each scenario, we add only a constant number of new variables and clauses. That keeps our reduction running in polynomial time and preserves satisfiability. Hence, any SAT formula can be turned into a 3SAT formula, completing the proof that 3SAT is nitrogen monophosphide complete. Now, when we have a clause, C with K is greater than or equal to 4 literals, written as X or X, we still want to break it down into 3 literal pieces without changing its satisfiability. Here's how. 1. Introduce K minus 3 new helper variables, Y, 2. Replace the single K literal clause with a chain of K minus 2 clauses, each having exactly 3 literals. First clause, X or not Y. Second clause, X or Y. Third clause, X or not Y or Y. Final clause, X or not Y. The trick is that each little clause passes the baton via the Y variables, so the whole chain is satisfied precisely when the original big clause is. In this way, we turn C into an equivalent C race, where every clause has exactly 3 literals, another crucial piece in our SAT to 3 SAT reduction. Now that we've converted C into CTUF, let's assert that CTUF is satisfiable exactly when C is. First, if CFRAF is true under some assignment, then each 3 literal clause must contain at least 1 true literal. Since the only new variables are the y's, the only way to satisfy every clause is to set at least 1 original x to true, so C itself must be satisfiable. For a formal contradiction, assume all x are set to false. Then, every clause in C, each a disjunction of 3 variables, turns out false regardless of how we assign the y's. In other words, C would be unsatisfiable, contradicting our assumption. Below, you'll see a concrete example of C+ built from C by padding each clause to exactly 3 literals with fresh y variables. Under any assignment that makes all x's false, each padded clause evaluates to false, showing that at least 1 x must be true. And that completes the proof that C+ is satisfiable, if and only if C is. Building on our earlier padding trick, we now show how to break any long clause down into a chain of 3 literal clauses, while preserving satisfiability. Suppose we start with a single clause, C equals all x or x. We introduce fresh helper variables y through y and form the conjunction C equals x or y, and Walik. These are Dedorstad. X or y, and Walik. X underscore or y underscore. So that every clause now has exactly 3 literals. Why does this preserve satisfiability? If the original clause C is satisfiable, at least one of the x's is true. We can then set each y to mirror that true literal passing the truth baton down the chain and making every 3 literal clause in C fresh true. Conversely, if C bring has a satisfying assignment, each of its clauses must be true. So at least 1 original x must be true, which in turn satisfies C. Thus we've shown C is satisfiable if and only if C is, completing our reduction to 3 SAT. Building on our previous reduction, we now show how to convert any SAT clause of arbitrary length k into an equivalent 3 SAT formula C without changing its satisfiability. Suppose C equals x or x underscore k. Introduce k, 3 fresh variables, y through y, underscore, k3, and rewrite C as the conjunction of k, 2 clauses, each with exactly 3 literals. C equals x or y, and x or not y or y, and x or not y or y, and x or not y or y, and x underscore k2 or not y underscore k4 or y underscore k3, and x underscore k1 or x underscore k or not y underscore k3. Here are the 2 key observations. 1. If CFIT is satisfiable, then in each 3 literal clause, at least 1 literal must be true. Tracking back through the chain forces at least 1 original x underscore I to be true, so C itself is true. 2. Conversely, if C is satisfiable, pick any true x underscore I, and then assign each y underscore j, so that this truth flows down the chain, making every clause of C true. Thus, C is satisfiable if and only if C is satisfiable, completing the reduction from SAT to 3 SAT. Now that we've completed the reduction from SAT to 3 SAT, let's quickly recap what we've learned. First, 3 SAT is just as hard as general SAT. It's nitrogen monophosphide hard, not any easier. We showed this by a polynomial time reduction that converts any SAT instance into an equivalent 3 SAT instance. The natural next step is to extend this argument. How can we prove that every KSAT problem for k is greater than or equal to 3 is also NP-hard? In the next slide, we'll tackle exactly that generalization. Now that we've extended nitrogen monophosphide hardness to all KSAT problems with k is greater than or equal to 3, let's shift our focus to the one case we haven't touched, 2SAT. In 2SAT, an instance is a Boolean formula phi in 2CNF, that is, a conjunction of clauses, each containing exactly two literals. The core question is simple: is phi satisfiable? In other words, does there exist an assignment of truth values to its variables that makes every clause true? Right away, two questions pop up. How can we check for such an assignment efficiently? And is 2SAT hard, or can it actually be solved in polynomial time? To make this concrete, take a look at the example formula on screen. Dot, not x or y, and not y or z, and x or not z, and z or y. We'll come back to this example as we explore both the structure of 2SAT and the algorithms used to solve it. Building on our example, let's dive into implication in 2SAT. In a 2SAT clause, if one literal turns out false, the other must be true to keep the clause satisfied. Equivalently, we can read a clause of the form not A or B as if A is true, then B must also be true. For instance, take the clause Z or Y. If Z happens to be false, then Y has to be true. In our sample formula, we have four clauses: not X or Y, not Y or not Z, X or not Z, and Z or Y. Notice how the last clause, highlighted in red, directly illustrates the implication not Z right, pointing arrow Y. Now that we've seen how each clause yields an implication, let's build the corresponding implication graph for the 2SAT formula. Not X or Y, and not Y or Z, and X or not Z, and Z or Y. First, we create one vertex for each literal: X not X, Y not Y, Z, and not Z. Then, for every clause of the form, not alpha or beta, we add two directed edges: alpha right-pointing arrow beta, not beta right-pointing arrow, not alpha. Concretely, from not X or Y, we get X right-pointing arrow Y, and not Y right-pointing arrow, not X. From not Y or Z, we get Y right-pointing arrow Z, and not Z right-pointing arrow, not Y. From X or not Z, we get Z right-pointing arrow X, and not X right-pointing arrow, not Z, Y. From Z or Y, we get not Z right-pointing arrow Y, and not Y right-pointing arrow Z. Together, these edges form the directed graph you see here, the core structure we use to check satisfiability in linear time. Now that we've built our implication graph, let's see how a single choice can ripple through it. Imagine we set X to true. To satisfy the clause, not X or Y, Y must also be true. Then, because Y is true, the clause, not Y or Z, forces Z to be true as well. In the center diagram, you'll spot all 6 literal nodes and their directed edges, with the path from X to Y to Z nicely highlighted. Below the graph, you can still read off our original 2SAT formula: not X or Y, and not Y or Z, and X or not Z, and Z or Y. The key takeaway? Once X is set to true, it transitively implies Z must be true too. Building on that idea of implication, remember, whenever X is true, Y must also be true. Yet, if X is false, Y can be either true or false without breaking the implication. Let's make this concrete. Take the formula, X or Y, and X or not Y. Both clauses force X to be true, but once X is true, Y can freely be either true or false, and the entire formula remains satisfied. In the accompanying diagram, you see the 4 literal nodes, X, Y, not X, and not Y, capturing all possible assignments and illustrating that at least one of them makes the formula true. Building on that, let's see how implication works in a simple 2SAT example. First, remember that X implies Y means if X is true, then Y must also be true. But if X is false, Y is unrestricted. Now consider the formula, dot, x or y, and x or not y. From the clause x or y, we get two implications, not x rightwards double arrow y, and not y rightwards double arrow x. From x or not y, we get not x rightwards double arrow not y, and y rightwards double arrow x. The diagram on the right is the corresponding implication graph. 4 nodes, x, y, not x, not y, with arrows for each of those implications. Notice that both edges out of not x point to y and not y, so if we ever tried to set not x to true, we'd force y to be true and false at the same time. That contradiction means not x must be false, so x is true. Once x is true, y is free to be either false or true. And indeed, both assignments, xy equals tf and tt, satisfy our original formula. Now let's see how an implication graph reveals unsatisfiability in a simple two-variable formula. Remember, each clause of the form A or B gives us two implications, not A right-pointing arrow B, and not B right-pointing arrow A. Here we have 4 clauses, x or y, not y or x, y or not x or not y. From these clauses, 2 critical cycles emerge. First, not x right-pointing arrow y, right-pointing arrow x, so assuming x is false, immediately leads to a contradiction. Then, x right-pointing arrow not y, right-pointing arrow not x, so assuming x is true, also fails. By the same token, y and not y form similar cycles. In other words, neither truth assignment for x or for y can avoid a conflict. Hence the formula is unsatisfiable. On the right, you see 4 nodes, x, y, not x, and not y, connected by directed edges for each implication. Whenever a variable and its negation can reach each other in this graph, it flags the unsatisfiability at the heart of the formula. Building on that implication graph view, we make a key observation. Whenever there's a path of implications from x to not x, and another path back from not x to x, no truth assignment can satisfy both. For instance, assume x is true. The first path then forces not x to be true as well, an immediate contradiction. On the other hand, if we start by setting not x to true, the return path forces x to be true, again contradicting not x. In either scenario, we hit a dead end. In short, whenever a variable and its negation lie in the same implication cycle, the formula is unsatisfiable. Now, building on our previous observation, we can use a simple graph-based test for unsatisfiability in 2 CNF formulas. We construct the implication graph and then hunt for any variable x for which there's a directed path from x to not x, and another path from not x back to x. If both paths exist, x and its negation lie in the same strongly connected component, so no truth assignment can make x and not x true at the same time, and the formula is unsatisfiable. Building on that, let's introduce the idea of a strongly connected component in a directed graph. A graph, or subgraph, is strongly connected when every vertex can reach every other vertex by following directed edges. In practice, we take a larger graph and break it into maximal subgraphs that satisfy this property. Here's how we find them. First, run a depth-first search on the original graph to record each node's finish time. Next, run DFS again on the graph's transpose, grouping together all nodes reached in each search. In the example diagram, you can see 3 such components outlined by dotted boundaries. Nodes A, B, and E form one component, nodes C, D, and H form a second, and nodes F and G form a third. Inside each group, every node can reach every other node in both directions, while links between the groups go only one way. Now that we've defined strongly connected components and seen how a 2-pass DFS can uncover them, let's explore 3 classic methods for finding SCCs in a directed graph. First, Kosaraju's algorithm runs 2 depth-first searches. The first labels vertices by finish time, and the second, on the graph with every edge reversed, pulls out each component. Next, Tarjan's algorithm collapses this into a single DFS pass. It uses one stack and maintains a low link value at each vertex to detect exactly when you've completed a component. Finally, Dijkstra's variant also works in one pass, but relies on two stacks, one to track active nodes and the other to track their roots. Although all three algorithms run in linear time, they each make different trade-offs in simplicity, memory usage, and implementation complexity. Now that we've surveyed the main SCC techniques, let's dive into the classic two-pass method, Kosaraju's algorithm, for finding strongly connected components in a directed graph G. First, we run a depth-first search on G and record each vertex's finishing time, F. Once that's done, we build the transpose graph G by reversing every edge in G. Next, we perform a second depth-first search on G, but here's the trick. We always choose the next root in descending order of the finishing times first from the first pass. Each DFS tree produced in this second pass corresponds exactly to one strongly connected component of the original graph. And since every vertex and edge is explored only a constant number of times, the overall running time remains theta, v plus e. Continuing from our overview, we first run a depth-first search on G and record for each vertex U, both its discovery time and its finishing time. Phase. Here you see our 8 vertices, labeled A through H, each annotated with its discovery/finish pair, C at 1/10, G at 2/7, F at 3/4, 9H at 5/6, 9D at 8/9. After we finish exploring C, we backtrack to B, which then finishes at time 16, while E and a wrap-up at 15 and 14, respectively. These finishing times give us a clear total order, B highest, then E, A, C, and so on, that we'll use in the very next step. Building on those finishing times, here you see two versions of the same node-weighted network. At the top is our original directed graph G, with nodes A through H labeled by their current scores. Solid black arrows show the original link directions, and we've highlighted a few key transitions in color for clarity. Below it is G, the transpose of G. Every arrow in the original graph has been flipped. Where G had an edge from A to B, G now goes from B to A. Likewise, for each connection between C and D, E and F, F and G, and so on. Notice that although all link directions reverse, the node identifiers and their scores stay exactly the same. This reversed network is what underlies algorithms that traverse edges in the opposite direction. Think computing strongly connected components, or running a version of PageRank on the reverse graph. Next, we'll use our total order of finishing times to guide a traversal of this reversed network. Building on the transpose graph from the last slide, Step 3 runs a depth-first search on G, but instead of picking the next unvisited vertex arbitrarily, we follow the finish times from our first DFS. On the left, you see G with each node labeled discovery/finish. Notice that B finished last at time 16, then E at 15, A at 14, and so on down to C at 10. As we explore in that order, each red oval on the left becomes one strongly connected component, A, B, E, C, D, F, G, and H. The blue arrows highlight the internal cycles within those components. On the right, we've collapsed each oval into a single node, AB, CD, FG, and H, and drawn all the edges between them. Observe how this condensation forms a directed acyclic graph. By following the decreasing finish time rule, DFS on G peels off each entire component in one sweep and reveals the DAG of strongly connected components. Building on our condensation view, here's the key correctness claim. Whenever you have two distinct, strongly connected components, C and C, and there's an edge from some vertex U and C to some vertex V and C, then the finish time of every vertex in C from our first DFS is strictly greater than the finish time of every vertex in C. In the left-hand diagram, each dotted region marks an SCCC on the left, C in the middle, and a third component down below. You can see an arrow leaving C and entering C. On the right, the condensed graph G treats each of those three regions as a single node, with edges from C to C graph and from both toward the bottom component. That strict ordering of finish times is exactly what guarantees we peel off and process each component in the correct sequence during Kosaraju's second pass. Neat and powerful. Building on our previous claim, let C and C terrace be two distinct, strongly connected components, and suppose in the transpose graph there's an edge from some U in C to some V in C terrace. We'll denote by f of C the finish time of C during our first depth first search. The key claim is that f of C is strictly less than f of C. On the left you see the original graph G with three SCCs, C, C, and a third component. Notice the arrows pointing from C into C, and from both of these into the third SCC. On the right is the transpose G, where every arrow is flipped. Now there's an arrow from C into C, and arrows from the third SCC back into both C and C. Because in GC can reach C breadths only via that single reversed edge, the DFS must finish exploring C before it finishes C breadths, which gives us f of C less than f of C. That ordering of finish times ensures that when we later pull vertices off in decreasing finish order, each DFS tree in the second pass isolates exactly one SCC, solidifying the correctness of Kosaraju's algorithm. Having shown how finish times order the SCCs in the transpose, let's see how the second pass puts that to work. Because we always pick the vertex with the largest finish time to start our second DFS, we land in SCC1 first. On the left is the original condensation graph G, where SCC1 points to SCC2 and SCC3. On the right is the transposed graph G, with every arrow flipped. In G, SCC1 has no outgoing edges, only incoming ones, so a DFS begun there can't escape into SCC2 or SCC3. It therefore visits exactly the vertices of SCC1 and no others. That guarantees each DFS on the transpose isolates one strongly connected component at a time. Building on our SCC decomposition, we now see a simple, efficient algorithm that shows 2SAT can indeed be solved in polynomial time. First, we construct the implication graph for our formula and compute its strongly connected components. Next, for each variable x, we ask, do x and its negation, not x, end up in the same component? If they do, yikes, we reject, since that indicates a direct contradiction. If no such conflict arises, we accept. And because we perform each of these checks in linear time over the graph, we conclude that 2SAT belongs to P. Building on that, we begin by constructing the implication graph for our 2SAT formula. Every clause, for example, x or y, yields two directed edges, one from not x to y and one from not y to x. Next, we identify the strongly connected components and contract each into a single vertex, giving us a smaller component graph. We then perform a topological sort on these contracted vertices. Finally, we traverse the sorted list in reverse order. Whenever we encounter an unassigned component, we assign all of its literals to true, which immediately forces every literal in the complementary component to false. Applying this procedure to x or y, and x or not y, produces a consistent truth assignment in linear time. Now let's turn our attention to Max2 SAT. In Max2 SAT, we're given a Boolean formula in 2CNF plus a target number k, and we need to decide whether there's a truth assignment that satisfies at least k of its clauses. The big question is, can this maximization variant be solved in polynomial time? For example, consider the 2CNF formula with four clauses, not x or y, not y or z, x or not z, and z or y. Max2 SAT asks whether we can choose values for x, y, and z so that at least k of these clauses are true. Building on that, here's our key takeaway. The Boolean satisfiability problem, SAT, is nitrogen monophosphide complete, and more generally, KSAT remains nitrogen monophosphide, complete for any k is greater than or equal to 3. The one exception is 2SAT, which we can solve in polynomial time. But the moment you switch to Max2 SAT, trying to satisfy as many clauses as possible, it becomes nitrogen monophosphide, complete again. In fact, in practice, we almost always care about these maximization versions, MaxSat, Max3 SAT, and so on, and each of them lives squarely in the nitrogen monophosphide complete world.